Hi, this is a quick movie just showing you some of the spherical aberration tools in AutoQuant and how you can improve your deconvolution by using these. Okay, so here we have a confocal data set. This is a Z stack. This is the XY view. Let's just have a quick look at the XZ and the YZ view. Okay, now I've already performed a blind 3D deconvolution on this data set. So let's just have a look at that. Okay, you can see a great improvement there, a lot of noise reduction. But when we look in the XZ and the YZ view here and here, we can see that really we haven't got a great result, because we know that this structure should be reasonably cylindrical, so it shouldn't look so stretched in the YZ direction. Okay, now a lot of this can be caused by spherical aberration. Okay, so actually, what is spherical aberration? Well, spherical aberration is caused when you have light rays from different focal planes arriving at the same focal plane, or light from the same focal plane at your object arriving at different focal planes when they're measured, like you can see in this image here. And this can be caused by changes in the refractive index. So when our specimen is embedded in a different refractive index to the immersion medium, inconsistencies in the cover slip thickness can cause it, and also very thick specimens. Okay, so how can we improve this? How can we correct for this? Okay, well, when we come into the 3D deconvolution dialog box here, there's a drop down menu for spherical aberrations, and at the moment we have none. Okay, so we're not doing any corrections. There are three different ways to do it. You can manually adjust the spherical aberrations from minus to plus 15. Okay, and you can see the point spread function changing here. We can actually auto detect. So if I hit this auto detect button on current, that will detect spherical aberrations on the current channel. It will attempt to automatically calculate the spherical aberration, but that's actually quite difficult to do, and it's actually much more accurate if you calculate it from known values. Okay, so if I go to this calculate tab here, it asks us for the specimen embedding refractive index. We already know the objective immersion refractive index is 1.515 because we used an oil immersion objective. But the specimen embedding refractive index is a little bit different. So that's the actual refractive index that your specimen is embedded in. We actually believe we estimate it to be about 1.4 in this case. Okay, and it's quite a complicated thing to calculate. It's a mixture of the refractive index of your specimen itself and of the medium which your specimen is embedded in. But for these values, any values that we give that are actually closer to reality will give a better deconvolution. So having a value of 1.515 for the specimen refractive index actually assumed that the specimen was embedded in oil, and so bringing it down to 1.4 as an estimate is going to give us a better result. Also, it's asking us for distance from cover slip in micrometers. Now that's actually the distance between the back of the cover slip and the first slice in your Z stack. Okay, and if you leave it at 0, it would automatically assume that your specimen is right up against the cover slip and there's no distance between them. So actually we've estimated that in this instance there is 3 micrometers between the cover slip and the first slice in the stack. Okay, so now if we hit the calculate button, it's calculated our spherical aberration here to be 4.35. Okay, so if we just minimize that dialog box and go ahead with the deconvolution, it's going to consider that spherical aberration while it deconvolves. So we're going to overwrite there, and hopefully we should see from using these estimates that we get a better deconvolution, both in the XY and especially in the YZ direction, where we see it stretched out in the original deconvolution. So let's just wait and see. You can actually also save the point spread functions, and you can compare those as well. You'll see a different point spread function when you use a spherical aberration detection, which I haven't done in this case. Okay, so here's our new deconvolved image. So now we have 3. Okay, so let's look at this at 100% and look at the YZ and the XZ. I'm comparing on my right here the original deconvolution with no spherical aberration detection, and on my left a deconvolution which considered spherical aberration detection. Now, just by looking at these, you can see that our image on the left is clearly better. Even in the XY, we can see that we've got a better result, we've got a better deconvolution, and especially in the YZ here, okay, we can see that we've got a much better result. I mean, if we could just compare those two images. That's just from estimating spherical aberration based on a couple of simple estimates. Okay, and when we look at that in the 5D viewer as well, we will also see a marked improvement in quality of image. Right, well, I hope that was helpful. For more information, please contact your local sales office or dealer. Thank you.